Okay, welcome back to the second part of the machine learning lecture. So the objectives of this part is you should know two ways of model selection, two ways of model interpretation, and two ways of how to compute the uncertainty. And you should also learn why we do model selection or why we should not do it, and that machine learning is actually not a black box, and learn why we need uncertainty and how we can validate this prediction intervals. So first we have a look at the model selection with first linear regression, with the lasso, or with the covariate importance. So first of all, should we do model selection at all? And if we talk about model selection, we understand it that we reduce the amount of covariates we have, and model building is the overall term, which means we select the relevant covariates and also the relationships of these covariates. That would be model building. And first of all, model interpretation is certainly much easier if we do model selection. And of course, if we have like noisy covariates, it's better to remove them. So we would like just to better use the really relevant covariates. And the computational effort is decreasing. If we have to calculate predictions for our study area from 300 covariates instead, or instead just 12, we would rather choose the just 12 if we could. And maybe it reduces our effort of computation in future. If you already know this was for this case study or for this study area, this was completely not relevant. So maybe we do not need to prepare all these raster data beforehand. But I was once talking to a theoretical statistician, and his advice was actually not to do model selection. So he proposed you rather use a better algorithm that deals with all your covariates instead of selecting a wrong model. Because it's if you select a model, it's always it depends on the data you have at this stage, and possibly you select the wrong covariates. So his proposition is to use all of the covariates, but to use an algorithm or a model building procedure that can deal with it. And from my experience, I usually, if I did strong model selection, really like having small models that are really open to interpretation, I would always lose prediction accuracy. The R square would always go down. So like a simple model, that's not all, I'd say it's not always the case, but it's often the case. The simpler model might also come with a lower R square. So,
what do you have like pure noise?
Say again?
Pure noise.
According to this theoretical statistician, you would still leave it in there, but the model takes care that it's downweighted. And I had within this models where I had 500 covariates, roughly 100 were pure noise, and most of the models were able to deal with it. Yeah, exactly. Exactly. You have all this. I mean, please, if you already know it's pure noise, don't add it at the beginning. But if you don't know and it's made, you can still keep it. But the model interpretation is hampered. It's having noisy covariates inside. It's no good for interpretation, of course. I don't know whether there is his name is Thorsten Hotthorn, and I'm not sure if he actually published like this in a sentence where you could cite it. So here I have a figure of this book of Garris. You have the interpretability of a model from low to high and the flexibility of a model from low to high. And it's clearly like something, a lasso or a subset selection of an ordinary least squares, like a reduced ordinary least squares. They are, of course, they're very small models, easy for interpretation because it's linear relationships. And as you go along down here, the models become complex and, of course, also more difficult for interpretation. So what strategies could we follow? I mean, you could, for example, ask an expert, what are the relevant factors and which ones do you think are not relevant? But from my experience, this helps, asking an expert helps in feature engineering, but not necessarily in model selection. Because they help you to derive new attributes from the geological map, for example, and introduce new aggregations there. But they will tell you, oh, this is not relevant, and in the end is one of the best predictors. Because from their knowledge, they have a process knowledge, which is not necessarily the correlation knowledge that we are searching for in these statistical models. And another strategy is just to remove the n worst covariates. And worst, we have just to define somehow by covariate importance, for example. Or we have a stepwise addition or removal of covariates. We could possibly test all the possible combinations. But once you are above, let's say, 20 covariates, you're out of this. Gets very computational, or we can use an algorithm that already brings a procedure like shrinkage in the boosting or lasso, like we've already seen this morning. So just for you to remember, the forward selection in ordinary least squares, you start with a model. Just with an intercept, then you try all possible covariates and take the best fitting one, and you add up covariates until the increase in R square or the decrease in error is below a certain threshold. And then based on cross-validation or even cite or cite likelihood, depending on the implementation. And the backward elimination, you start with a full model, and you start stepwise to remove the worst covariates, usually the ones with the highest standard errors, or like the lowest, or if there is a significance test, you take the ones that are not significant, you remove them, and then you continue until a certain threshold is reached. But for these forward and backward selections for linear regressions, they're very straightforward, very easy, and to understand, it follows a certain selection path. So it's also not it's usually easy to compute. Doesn't take too much effort, but it is binary selection, as I already mentioned in relationship with the lasso. It's just covariate is in or it's out, and it doesn't take care of the correlation in the covariates. If you have multicollinearity in your data set, you usually have a problem with such a procedure. And it likely overfits your data, because it likely takes the effects to be too large in the end. And in this problem, if we have more covariates than we have observations, we cannot even fit the model. And I mean, there are simulation studies that have seen if you start with a true model of a linear model, then you add a little bit of error variation, and then you do model selection with stepwise forward and stepwise backward. These procedures never find this true model again. It is a biased model selection procedure. So it's some sort of also arbitrarily removes good covariates. So a better strategy would be to use this regularization, this shrinkage that I introduced through Lasso. And this is the same graph as from this morning. It's basically if this shrinkage factor increases and you put a large penalty on the coefficients, they start to get smaller and smaller and eventually drop to 0. So the ones that drop to 0, the covariate is completely removed out of the model, and the ones that are just like hold smaller, they are still able to contribute to my model, but only to a smaller part. So this reduces then the overfitting risk. So, but this brings me now to the covariate selection that can be introduced for random forest based on removing the n worst covariates. And just for you to remember what was again this out of bag error, we have this resampling procedure in random forest, and there certain samples are not taken for a certain tree, and then we can compute like a cross-validation error that is here called the out of bag error. And we have in tree-based procedures, we have covariate importance, and just want to draw your attention that we have like 2 types of covariate importance. One is basically evaluating for each split, if a covariate is involved, how much does this covariate reduce the error by adding this split. So it's oriented on the fit of my tree. How much is this split improving the fit on my calibration data? The second variable importance is done like this. You have a covariate and you keep permuting or shuffling around the values of this whole covariate randomly, and you check how much you have a drop in your prediction in the end. So you have for like one covariate, you keep permuting the values, so it becomes some sort of a noisy covariate and should not contribute anymore. So, and then like this, you can check how much prediction accuracy you lose. This is, you have a larger effort to compute this because this permutation has been done repeatedly, but it's oriented on your predictions. So usually the difference, it's not so big, but if I could recommend, if you're interested in good predictions, you might better want to use the permuted covariate importance. This is this variable drop out and then computing the loss in R square is used for, this is a procedure also used in linear models. I not really recommend it because you change the complete structure of the tree, or I mean, this means you would need to refit a complete new model. And if you have correlated covariates, one can replace the other, and the drop might not be so big just for removing one of this correlated pair. But still, they as a pair we will see this later on, will be most important. Removing removing one covariate and check the drop in R square, I recommend to apply for methods that do not have another means of computing covariate importance. So these are just for one example. These are this covariate importance. You get this type of plot, and now if we want to select covariates based on that, we can easily do a backward selection on it. So it's called like recursive backward elimination, and you remove the worst covariates, that the ones you have here at the end, and you refit the random forest, and you keep doing that until you computed the whole path. Hanna also showed in her package cast, there is an implementation of a forward selection, also based on this covariate importance, but I've not checked it out in detail. I think she breaks off at a certain point and does not compute the whole path. So, but for both methods, it's the same. It's true like for stepwise with ordinary least squares. There is always a risk of removing a good covariate because because of some other noisy covariate, it was graded a bit lower, and then you remove it. There's always a certain risk that you remove something that should not have been removed, or your model in the end gets too small and you have an underfitting situation. And a further problem that we have with this covariate selection, if we really have like strongly correlated covariates, they will both be graded like with a high importance, and they will both not be removed. So a procedure that is like decorrelating the covariates would also need to be implemented. But I'm not aware of I'm only aware of an ad hoc approach that the master student of Andreas once implemented of removing these correlated covariates. I'm not aware of software that does this properly yet. So here this is now an example of the whole selection path. This is just the number of covariates remaining in the model and the out of bag error. And for this example, and also for a lot of my examples, the number of covariates actually remaining, or where you have an optimal or like a minimal out of bag error is usually quite low. So the model selection with this recursive backward elimination, it's quite straightforward, easy to understand, easy to implement. In the exercises, it's just like an iterative loop function, and it's in that sense efficient. It removes a lot of covariate. You have like a very sparse model in the end. But as well, it's also a little bit an ad hoc procedure. You don't really know if you have the good model in the end. As I said, the correlated remain in the model. If you have only like, you start maybe with 100 covariates and in the end you have just 5, you might end up with having artifacts in your predictions. Because then it starts to partition only on 5, and if these 5 are just like the geological units that are very coarse, then you have like value jumps in your final maps in the end. And as I said, stability is unclear. I'm not too sure if there is a proper theoretical foundation of this type of covariate selection. Might be biased, might be not choose the right ones. And it's time consuming because the next step always depends on the previous one. So we cannot do any parallel computing. And maybe you have had a lot of computation effort and maybe also some programming effort, and in the end, just a smaller model, no gain in accuracy. This has to be kept in mind. So, are there any questions on model selection? Yes, but this means if the out-of-bag error decreases, that doesn't mean that you a fully independent test set will have a decreased error. Because some sort of, if you do a lot of data operations, there is every data point has contributed to at least that one step to your final model. So they are also these out-of-bag errors at a certain point. They're not independent anymore. They're only independent from that single tree where you compute it. But beforehand, if you already took many decisions based on the out-of-bag error, you start to adapt to your training data as a total. And so, I mean, out-of-bag error is like a mean of optimizing your model, but like the final proof of performance should be done with a fully independent test set. Further questions? Then we go to model interpretation. And here we can use partial residual plots. Those are used for method in the connection of the linear or the additive framework. And they are constructed basically by plotting the residuals plus the effect of the covariate you want to have a look at versus the value of the covariate. And the partial dependence plots, they are basically, you can use them for any kind of other model. And they're not just limited to the linear framework where you have like clear residuals and clear relationships. And they basically work as this, that you fix all your other covariates and you just vary the covariate that you want to have a look at. And then you check for the relationship regarding your response. Here is an example of, at the top here, you see exactly, or no, all of these are partial residual plots for the lasso, for a geostatistical model, and also for a nonlinear parametric model, for a gamma. So this is basically the effect that is fitted into this. Here you always have the values of your covariate, and here you have the difference in residuals plus, again, your effect. And this gives you then the direction of course, in a linear model, you would also see the direction of the relationship on the sign, if it's a plus or minus coefficient. But for these nonlinear models, you can have quite an easy interpretation. Here, this is just for a categorical covariate that I used here. This was, I introduced the sampling date into my model to correct for this long sampling period. And then you can see just the different effect of each group of sampling dates. The partial dependence plot, you have again here on the x-axis the value of your covariate, and on the y-axis you have the value of your response. And this here was, again, it was a clay content, and clay content usually varies from in my data set from, don't know, 5% to maybe 40%. But I can see the effect of this covariate did only vary within like this 26 up to 28% of my clay. So only in a very narrow range of my value range of my response. And what I can see is the relationship is like jumping. So this means the trees always split it roughly on the same value of my covariate. So it's always roughly around 4 of this terrain attribute of the value of this raster that the splits were taking place. So I could some sort of, this shows me now I could some sort of also have added a binary covariate and it would have roughly been the same. And of course, for the categorical covariates, they again give me like the meaning over this category. It depends a bit on the package you use. Like for linear models, there is a function called that's even in basis in partial or a partial plot. And but that's all in the exercises. And for the randomForest package itself, the one, not the Ranger one, that had the function implemented as well. The Ranger one doesn't, but there is another package that brings it in. It's the DPD package. And I mean, if you have this relationship between your response and your covariate, you can even, there is a publication, you can even start to map your relationship into space. So you can see, like here, the original covariate. This is the curvature in a certain area, and this will then be the partial dependence. And in this publication, they also mapped like the local importance of the covariate. That was not the same throughout the study area. Just to be complete, I've myself never plotted these plots, but it's even possible to have like a spatial interpretation of the dependence of your covariate. So that's how we can like find out the relationship. Are there any questions so far? Just as a side remark, I mean, if these plots are nice, but if you have like 50 covariates and you don't know which ones are the most important, it's very difficult to, you cannot really have an interpretation of 50 covariates. So these, like starting an interpretation means also you have to have a certain ranking to get a better understanding. This means you need a covariate importance, or you need to do some model selection beforehand. But this again means also like everything that has been removed from the model, there is a certain, it has to be taken into account in the interpretation. For example, if you have elevation and temperature highly correlated, if then you cannot just state in the interpretation, oh, it's all temperature related. It might be just an elevation gradient.
I mean,
yeah, this can be done. These are the plots at the bottom. Or this would mean you need to introduce an interaction of male-female with your regression curve. And then you have the estimation of two different curves, and then you can plot it again. This means you need a different specification of your model to actually get an estimation of that effect in your model. The local importance is taking into account the covariate importance, but I exactly don't remember how he computed it. But the plot in the middle is basically like plotting onto the map this relationship. And the other one, he did some additional calculations to produce this map. It's just for this covariate. Most likely because for you know where the covariate was implemented in which splits, and if these nodes in the end contributed to this prediction. And like that, you know if in a certain area a covariate was actually used for splitting or not. So then we go over to model uncertainty. And here I'd like to stress the difference between confidence intervals and prediction intervals. And most of you are likely aware of confidence intervals that are usually they are intervals that are computed with an estimation. For example, an estimation of a mean of a population. And then you have a confidence interval that goes along with that mean estimation. And it's basically the confidence interval evaluates the uncertainty you introduce in your model because you don't know the real value of your coefficient, because your coefficient in the model is just an estimation. And if you want to compute prediction intervals, it's not just about knowing the mean, it's knowing a new observation. And of course, this is much more difficult to predict, like someone's shoe size just here in the front than just the average shoe size in this room. So for a prediction interval, you also have to take into account the actual model error, not just the error that you introduce by your uncertain model estimation. And one idea that can be used for machine learning methods that do not inherently already have a procedure to do that is a non-parametric bootstrap. And the idea behind that you have a total population, for example, sampling all of the soil in one study area, and then you take a sample of that population, and if you take again a sample of that population, the assumption is that you have you retain the same distribution. So if you have here an unbiased sample and you take here a sample of this sample, you keep up the same distribution of your data. So this brings us what we've already have seen with the bootstrap aggregation or the random forest. This brings us basically to these resampling procedures. And this means with this resampling, we can start to approximate our distribution of our final prediction. And it's basically useful to do aggregation or these ensemble learners, as we have seen this morning, but it's also useful to compute the uncertainty in a model. And that's basically how it works. It's now a non-parametric bootstrap, so we do not take any assumption of the distribution of the data. It's basically we take the data as it is. If it's positively, it's very positively skewed, it is positively skewed. And we resample. This means we take a random sample with replacement of the same size. So the same size is to be taken because this retains the property of model fitting. A model fitted to just 100 points is something different than to the total data set of 150, for example. And then we fit our complete model building process. If you did some tuning, you have to do that tuning also on this resampling. And we repeat that many times. So I'd say at least 500, a bit more would be even better. And then we can compute predictions from all of these 1,000 models. We have predictions, and this gives us, for each point, gives us like 1,000 predictions and a full distribution of for each pixel where we can compute the prediction. And with this distribution, we can now continue to, for example, derive a 95% interval, derive a mean in the sense of a model averaging, or an 80% interval, or whatever we need in the end. Or a standard deviation, of course, as well. So the quantile regression forest is exactly such a non-parametric bootstrap. As we have seen, to grow this large number of trees in random forest, we already do a resampling. And this means that the random forest algorithm already has this bootstrapping inside of it. Therefore, what needs to be done is basically there were just small changes needed in the algorithm. They just need to keep back all the samples that have been together in a leaf. So like that, we are then able to compute the full distribution, because we can look up for every sample that has been together in a leaf. And so, for example, we have here the first tree of resampled data, and this data point gets into this leaf, for example. And then in the second resampling round and the second tree, this data point ends up in a different leaf, of course, because the tree has a different structure and ends up with other data points. And of course, now we take all these data points together with it, and from all these data points, we can then construct this full distribution or these intervals we need. And here you can see the colors indicate like higher and lower values. Here it's well sorted, this leaf. Here it's less well sorted, so our distribution is already, by adding this tree, is already widening. Now, there is also an approach called model-based bootstrap. This is usually used if you already have an assumption about a good model, and we have an error distribution that we can work with. So it's basically we do not a resampling of our full data, but we just do a resampling of our errors in the end. So this sum of the function of x is basically the complete model summing up all the effects of my covariates x and in space that have a location in space. So, and what we do is basically simulating a new response vector that where we add at random this error, that part that we cannot explain in the model. So this means our response is then not the same anymore, but we take a variation under the assumption of the part that we cannot explain in the model. And again, to this newly simulated response, we fit our full model procedure. And again, we have to do this many times as before. And we have like 1,000 models, and again, we can compute 1,000 predictions. And this gives us again the full distribution at each prediction pixel. It's a bit more complicated than that to compute these responses and the error, but I think I skipped that now because usually, usually the model-based bootstrap, I'd say, is much less used than the parametric bootstrap. And we have now looked where we use which one. And the non-parametric bootstrap is basically not taking any assumptions about any true model or any good model and any error distributions. But if you do not have a lot of data, it might still it might fail, because I mean, a simulation with 1,000 repetitions might be not a good idea to start with just 50 data points. And there, I'd rather go with a parametric bootstrap, with this model-based parametric bootstrap. And disadvantage of the whole system is there is mostly no software. There is a package called boot, but I've not tested it myself if it really does what it should. So usually you have to do the implementation yourself to gain the uncertainties. But on the other hand, a non-parametric bootstrap, if you are able to fit one ranger model, you should be able to fit 1,000 ranger models. It's just find an apply function, find something that can compute parallel, and then you're done. But it's, of course, it's very computational intensive. CPU mainly, depending on your data set. And the model-based bootstrap, for me, the prediction intervals, I mean, it really depends on your model. They might be off. In my case, I used this approach. They were usually a bit too narrow. And again, there is mostly no software. You have to do it yourself. And I'd say it's slightly trickier to implement and to correctly do it. And all of these approaches are basically quite computationally intensive. But altogether, even if it's computationally intensive, a prediction that does not come with an uncertainty map along with it is nowadays is nothing you can publish. Just an average, like a mean prediction, it always needs an uncertainty related to it. And any reviewer or end user should not accept anything else. So, yeah. Ask your boss for a larger computer. Now, if we have computed these prediction intervals, we also want to know, are they actually any good? And one way for evaluating them is basically you have a test set and you check if you have a 95 prediction intervals, if really like actually 95% of your data points in your test set are inside these intervals. And you can then, for example, create a plot like this. Here I have the values of my response. This is pH here. And I just order the predictions to get an easier view of the plot. I add the prediction intervals. In this case, they were quite symmetrically. This doesn't have to be the case, especially with a non-parametric bootstrap. Here they came from a model-based bootstrap. And then you can add your observations from your training data, and you basically check which ones are outside for this 95% prediction intervals. And instead of just doing it for a 95% prediction interval, you can basically do it for all kinds of, you iterate through all possible intervals. And to properly see where you actually lose your, where they fall out, if they are like falling out below or above your value ranges, it's better to compute one-sided intervals. And with these one-sided intervals, the nominal distributions, that's what the interval said it should be, and the actual coverage here, it should follow then the one-to-one line. And here it was in the end, it was not too bad, but here the coverage was a bit too high. This means there were too many values of the test set were at the lower ends of these intervals. So here I have an example where I compared the model-based bootstrap of a GAM, where I have a 90% interval, and in the end I had 15 or like 16% of my data points were outside. So I had a bit too many that fell outside. So my prediction intervals were a bit too narrow, a bit too optimistic. And the quantile regression forest had a bit a better fit. There were roughly like 9% outside. So I'd say these intervals performed better than. And we can also see this here in this plot. This follows much better the one-to-one line than this one, where we can see we really lose the data points at the lower end here. And in the end, as a result, this is a prediction for one of my study areas where I have the clay content, the mean prediction, and really at every pixel you can have this full distribution. And for every pixel you can now start to, depending on what your end users need, maybe this is a plugin for a further error propagation in their model. Maybe you compute the width of such a prediction interval and hand it over to some end user, or you even for areas where you have like a large prediction interval, you say, okay, this cannot be used for a certain decision, and you can mask this map. For this area, create no prediction, for example. So as a brief summary, we have seen we can do covariate selection with the lasso, with the shrinkage of the coefficients if they fall to 0. We can also use the covariate importance. We have seen the partial dependence plots that are available to any kind of model. And we have seen how to compute the uncertainty with prediction intervals. Now, are there questions so far? I did not properly hear. No, I have not tested anything of that. Anyone here? Now, just to end up, I summarized some personal tips for your modeling career. I mean, bless you. Don't believe that there is just one solution. There is, from my experience, it's clear that it's not just like one machine learning tool that rules it all. And this means you have to properly understand your domain, you have to properly understand the end usage of your product, and according to that, carefully choose how you proceed. And do not neglect classical statistics, because throughout my 2 lectures, I referred quite a lot to ordinary linear models. Without the proper understanding of that, you will also fail a proper understanding of machine learning tools. And if you find all these methods quite hard to understand, maybe in the end it's better to implement a method that you properly understand, but is a bit less complex. But then you are sure you do not fail in the application. It's maybe better to use a simpler model, but you are sure what you're doing than applying complex stuff, and in the end it's completely off. And do not neglect domain knowledge. It's really like invest in asking experts what could be relevant. They help you with feature engineering. In the end, investing in like talking to them and being able to build models might help you more than tuning the latest and try. Or at least that's my experience. So some further literature on bootstrapping and categorical responses if you work with that. And what's very useful is this chapter 8 and the package verification, especially if you work with categorical data. It helps you to compute the validation statistics. Okay, we continue with the exercises again. So as a first step, I included the selection of covariates, then second model interpretation, and the uncertainty with quantile regression forest. So first, this is the list of packages we use. It's basically the ranger. This is for the lasso. This is for the data set plot, and previously I could ask whether there is a package for this partial dependence plot, this PTB. So we load in the data as before, basically load the packages, load the data, and again select this pH response, and again select the covariate. Then I set the seed to make it reproducible, the random forest, and I fit a ranger, a random forest with this ranger function. And the importance, I select the permuted one. So I have a, I have a ranger object now. And from that, I can easily plot the covariate importance with, I use here the ggplot. And now you have here the names of the covariates, and below this is covariate importance based on permutation. And the names of the covariates, it is not properly documented in the function because it were just too many for the help page. But all of them that start with CL are climate data, and because it's my data, I just know this RR is the precipitation. And we see here the yearly precipitation and the March precipitation and the November precipitation, they all rank highest. And of course, the precipitation pattern of these months and the yearly pattern are correlated. So we can now see exactly the problem that they could actually be replaced most likely. And maybe we could now try to remove the monthly precipitation patterns and just use the yearly one. And just from knowing that the yearly precipitation is a better covariate for interpretation, we remove the other ones that are more difficult for interpretation. This is a relative measure of covariate importance. I'm actually not too sure what is given back here by Ranger. If this is standardized or if it sums to 1 at the end, I've not checked on that. But for my interpretation, I usually don't use these absolute values. I just used like the relevant relative shift. So now now we have this plot. It continues here where we remove step by step, and since there are so many covariates, I decided to remove like the worst 10, and once my set gets smaller, just the worst 5. And that's why I build up a sequence like this here. So this is basically the number of covariates that are fitted, or the model is fitted to these numbers of covariates. But always like the worst n is then removed. One could also just remove one by one, but this takes then really a long time. And this part is quite a bit of, I would say, old-style programming, because each model fit depends on the previous one, so you cannot do proper parallel computing. So that's why I just used in R usually very inefficient for loop. Here I set up the objects to collect my results, one for the error and one for the quantile regression forest with the eliminated, just for the model objects, with the eliminated items. I start with the first one and set the selected covariates on. And then I have a loop that goes over my sequence that I just had beforehand here. It's the number of covariates to retain. And here I compute the variable importance, and I have to order this variable importance, so decreasingly. And then I keep just the names of the most important ones, up to this number of covariates that I want to keep. And then I collect the models in this list, and I collect the errors in this list. So at every step, a new item is collected there. I'm not sure if I should run that, because I think it takes quite a while. Let's try anyway. We'll see. Basically, in the end, I can then build a data frame with the number of covariates and the out-of-bag error. And this gives me this plot here. The number of covariates, out-of-bag, and somewhere there is a minimum. But as you can also see, it's a bit, it's not such a stable relationship. It's not clearly like decreasing or increasing, it's hopping around a bit. So if you just fit like one single model, you can also just say, okay, maybe I keep some more or I keep some less covariates. From my point of view, you do not really need to cut at the minimum out-of-bag error. If you need to fit a lot of models, then you want to have an automatic rule that does not need user interaction. Let's check, it's still calculating. So, I mean, the exact same procedure can be implemented for the geoGAM that we have used this morning, this boosted regression trees. There you also have a variable importance. You can just do recursive backward elimination. Any questions so far? Then I would have finished now. What results in this plot here. Now, the first part shows this partial residual plot, and I basically, the function is called turn plot, sorry. This is in base R even, and here I just used like a linear model with some of these of the main covariates, and I fit them to compare the effects to the lasso. So let's see. This gives me now for an ordinary least squares fit this partial residual plot with the straight line being the effect. And now we can do exactly the same for the lasso. We have to set up the lasso as in the exercise of this morning and choose the index. And here we have to create a plot manually because there is no function to plot it ourselves. And the effect is roughly the same of this covariate plotted in, but it's for the lasso, it's slightly less steep. And I mean, this is obvious since the lasso is putting a penalty on the coefficients, so we expect them to be slightly smaller, depending on the value of the penalty of this lambda parameter. But at the same time, we can also see the data points here. We have really a large scatter. So the relationship of my response to my covariate is not so good in this case. Of course, if it would be a good relationship, all these gray points would really scatter around this red line. This is also an indication it might be not such an important covariate. But altogether, this data set, the response covariate relationship is rather weak. So this is to be expected. So this brings me to the partial dependence plot, with where I basically select the model here that had the best performance above with the minimum out of bag error, and I select again the importance, and I take the 6 most important ones for interpretation here as an example. And this the function is called partial plot, and I first have to compute this partial relationships. And I basically give the object of Ranger. This package accepts Ranger objects. I give the training data and the name that I just that I extract here or hand over here is this function over from this list in this lapply function. This is basically making it automatic to 6 times create a plot. And since this plot partial returns this lattice or trellis plots, I have to use grid arrange to get them on the same plotting device. So I can run them now. So these are the 6 most important ones here. It takes now a while to compute these partial relationships, but now it's done. So now we have these relationships. Here we have the precipitation, and on the y-axis, it's basically the original values of my pH response. And here again, I have this this categorical covariate, and the others are continuous covariates. And now, what do you think? Are they well splitting or not? Are they good covariates or not? Just overall, if it would be really good covariates, I would expect to have splits over the whole value range of this covariate. And now we see major splits here, and for basically for all of them, there is one value that takes nearly all of the splits. I would prefer to really have a covariate that splits all over the values, and so this graph would be a bit more expanded over all the values, and not have like a steep jump here. But what's interesting, we have an opposed relationship for this one here. Those, but this is some other climate variable, which is this is the global radiation compared to the precipitation, the RR. They all have nearly the same relationship, like first high pH values, then other, and the other is just like the opposite. So now here we can build the quantile regression forest model. This is basically done by, again, this function ranger, and it now, since a year and a half or something like that, it can also fit the quantile regression forest directly by just setting this quantreg option equals true. And what it does, it basically keeps back, it uses more of your memory. It keeps back all these values that have been together, or the indices of the values that have been together in one leaf. And like that, it can then compute the distribution for every prediction. So then we fit this ranger model again. We select the validation data, and we predict the mean for the validation data with this quantile regression object that we created here. And here, to create these distributions, we basically have the same call, also data, but you have the type quantiles. And then you ask for which quantile. If you just need to compute prediction intervals for a certain quantile, then you just take this. But here I computed like a whole range, so I have the full distribution. And then here at random, I just select one site, and one can produce a histogram of this distribution for this one site, at this validation site.
Right. So is that over or?
I don't think so, because my data is this data was mainly sampled in the 70s. The study area is quite big, and the relationship between my predictors and my response is rather weak. So it's feasible. And also in the validation, when I checked if like how many data points are outside of a 90% interval, it would fit roughly. Yeah. Yeah, maybe 4.5 or 4 to 8, something like that. But still, I mean, it's like a pH range that's, yeah, maybe I have to add the. Oh no, that's the other plot. This I have the 90% interval. I mean, it is quite wide, but that's what it's to be expected regarding this data quality. Basically, the quantile regression forest is a non-parametric method. It does not assume that you have like symmetric prediction intervals. And this is completely feasible from my point of view. And it's also, also something I want to have in my prediction intervals in the end, because they are most likely I cannot assume a distribution for them. I cannot assume they're Gaussian. Exactly, here I have the dashed lines here are the 90% interval. It's, yeah, from 6.2 to 7. For this point, I'd say it's still okay considering the data quality. But just because these intervals are wide, it's not a reason not to hand them over to the authorities. I would discuss that with the end users.
Okay.
Because I would try to explain them uncertainty, that would be the first task, the communication of what do we see here. But taking weather forecast as an example, I think it should be easy to understand. And then as a second step is the question, how can you work with that now? How can they in their work like deal with this uncertainty? Do they want to take decisions on of a map with a certain uncertainty or not? But they have some sort of also to, one has to define the threshold, I think, together with the end application. So then I basically also produce this type of plot. I just reached that now. And this means regarding this validation of these 90% intervals, the intervals are even too narrow. So because I have, for a 90% interval, I have 16 instead of just 10% outside. So intervals are wide, but still too optimistic. And this is basically, takes a lot of code to produce that. And here also this, you basically compute all of the intervals, created a sequence, and then you also can compute this plot here. Yeah, that's all of it, how to get these intervals and how to validate it. Let's check no questions here. Any further questions? And I mean, I'm still around, so don't be shy if you have problems with the code and so on. I can explain in detail.
We don't have any comparison without like with the perfect machines or also.
No, I just used because the quantile regression forest you just have to set in Ranger, you have to set the argument quantregForest like equals true. For a support vector machine, you would need to implement the bootstrap approach yourself. So that's why I don't show it here. It will take more coding, and it's more computational intensive. Any further questions? If not, we are done, and please ask questions also later, individually, no problem, and hopefully you enjoyed this tutorial.
Or event in Europe in the world where somebody wants to boost statistical learning skills, where would you recommend that you go?
How do you mean a good conference? Where to go?
Yes, like what's a good place to see some up-to-date developments and some problems and operational tools.
Myself, I mostly follow the conferences that are within my subject and domain, but I've not followed it, but I'd say the UseR conference would be a good choice. But there are other conferences like the geoGAM or like the GSTAT, but they are quite technical, I'd say.
Almost 1,500 people now. This year's last year, it's 1,000 people. It's like I recommend this for with the application developments. So you have to look at the often there's like application in medicine and like some maybe operation data or really different methodology. But you know, you look at the next, sometimes it's very generic problems and uncertainty, bootstrapping and very generic, so it doesn't matter, that's not your only application, but you can learn a lot. And then you go, of course, the only packages. So if you want to really know what's happening and to solve something and then make a package. So yes, how you can use that. Anything else?
No.
Okay. Well, thank you. One more time, thank you so much. And I see Madlene was connecting with the RStudio server, on her server in Bern. It's a nice server. Can you show us the configuration?
I mean, it's basically you get an RStudio window within your browser, and it's now, I mean, all I did here, it's computing in Bern. And we have a high performance computer behind it. And so, and if you close that window, you can go home and open it, it's still at the same place. So it's easy maintenance, and the configuration. I don't think you see too much.
So it's the 87 threads. And how much RAM do you have?
1 tera.
1 terabyte now. Okay, so you can put everything in RAM, right?
Yes.
More or less, and you don't have to save on local objects. You just do all the stuff in RAM, and then you just get active.
We would also have GPUs to compute on, but I myself am not yet capable to do it.
Okay.
Because it needs some setup.
Yeah, pretty sure when you do it later, so they have to use setup. But that's good Java. Yes, so you see that's nice. That's a nice hardware. Eventually, now you can be whatever you like, but you have to get the job done. You have to also get some hardware. Although you still need Lambda, you will combine these machine workstation and Google retention. And also at low cost and good models and everything else.
But also, I mean, the RStudio server itself, it comes really at the convenience. And if you can persuade your IT departments at your universities, please ask them to install it.
Okay, thank you so much. We stop now. You can stop also.